In this problem, three coins are tossed. First question is we are asked to write down the possible outcomes when three coins are tossed. So the shortcut here is 2 raised to 3 because a coin has two sides and they're tossing it 3 times. So you'll be getting 2 raised to 3. There will be 8 possible answers as given below: head, 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 and tail, 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 tail. So there are 8 of them. For the next question, the coins are biased. For each coin, the probability of getting head is 2 out of 3. A random variable x is defined as the number of heads when 3 coins are tossed. So we are asked to find the probability of getting a tail. So that will be 1 minus 2/3, or the complement of 2/3. The answer is 1/3. For part 2, we are asked to find or to complete the distribution table for the number of heads. So it could be zero head, 1 head, 2 heads, 3 heads. So for the first one, we're getting the probability that there will be 0 head. That could only mean you will have tail and tail and tail. But the probability of getting tail is 1 out of 3. So getting 0 head or tail and tail and tail will be 1/3 times 1/3 times 1/3, which is equal to 1 over 27. If you're going to use your GDC, you can find it using binomial PDF, where you encode the value of your n, which is 3 tosses, and the probability of getting head is 2/3, and x value is 0, meaning to say 0 head. So you will be getting an answer which is in decimal, I think, which is 0.037037. Now, if we need to give the answer in fraction, you can approximate it to fraction by pressing menu number approximate to fraction. That will also give you an answer which is 1 out of 27. Now to get the probability of getting one head, so that will be head, tail, tail, or tail, head, tail, or head, tail, tail, or tail, head, head. So there are 3 possibilities in all. For one head, you can have 2/3 head and tail, so that will be 2/3 times 1/3 times 1/3, that is 2 out of 27. But since there are 3 possible combinations, you multiply this by 3, you will get 6 over 27, or in lowest term, 2 out of 9. To get the probability of getting 2 heads, so that will be head, head, tail, or head, tail, head, or tail, head, head. So 3 times of 2/3, 2/3, 2/3, and 2/3, and 1/3, 3 of them. You will be getting 4 out of 9. So just continue doing it for 3 heads. That will be head, head, head. So that will be 2/3 times 2/3 times 2/3 equals 8 over 27. Okay, so that completes our table or distribution table. Letter C, hence represent the probability distribution for x in the graph. So I just use decimals here, but of course you can use the graphing calculator. You can use the spreadsheet of your calculator. You label your x as 0, 1, 2, and 3, and your y or p of x as 1 over 27, 2 out of 9, 4 out of 9, and 8 out of 27. Then you find the graph of this or scatter diagram, and you copy it from your calculator. In problem number 2, Cecile plays a game involving a biased 6-sided die. The faces of the die are numbered 1 to 6. The score of the game, x, is the number which lands face up after the die is rolled. The following table shows the probability distribution of x. Now we are asked to find the exact value of p. So the exact value of p will be the sum of all the probabilities, which is equal to 1. So we have 1/6 plus 1/2 p plus 1/8 plus 3 halves p plus 1 over 12 plus 3p equals 1. You can use your calculator to find that p is equal to 1 over 8. You can use your algebra, menu algebra and numerical solve. In letter B, Cecile plays once, calculate the expected score. Here we are going to calculate the expectation of the mean or the expected mean, which is the summation of the scores and the probability or corresponding probability. Our solution will be 1 times 1/6 plus 2 times 1/2 times the value of p, which is 1/8, plus 3 times 1/8 plus 4 times 3 halves times 1/8 plus 5 times 1 over 12 plus 6 times 3 times the value of p, which is 1/8. In all, the total is 49 over 12. For the third problem, Cecil plays the game twice and adds the score together. Find the probability that the sum of the score is 4, giving our answer as a fraction. So if Cecil plays the game twice, we have to look for the possible numbers which will have it face up when it lands on, let's say, on the floor. So if the first die on the floor, on the first game, it lands on 1. On the second, it could be 3 because the sum of 1 and 3 is 4. Another possibility is the first landing on 2 and the second on 2. Again, the sum of the score is 4. Or the first landing is on 3 and on the second it's 1. So these three are the possible combination to get a score of 4. 1 and 3, or 2 and 2, or 3 and 1. Now we get the probability that it lands on 1. We look at the table, it's 1/6, and the probability of it landing on 3 is 1/8. So 1/6 and 1/8, or 1/6 times 1/8 equals 1 over 48. For 2 and 2, so the probability is p is, we know the value of our p a while ago was given as 1/8. So 1/2 times 1/8 is 1 over 16. So 2 and 2, 1/16 and 1/16 equals 1 over 256. And another, or the last combination will be 3 and 1. 3 is 1/8 and 1 is 1/6. That gives product of 1 over 48. So 1 and 3, or 2 and 2, or 3 and 1, or implies addition. So we get the sum of all these scores, 1 over 48 plus 1 over 256 plus 1 over 48, and the answer is 37 over 768. The answer is given as a fraction. During a season, a basketball player has an 85% success rate in shooting from the free throw line. In one match, the basketball player has 20 shots from the free throw line. A represents the random variable as x. Our answer is a random variable x is equal to the number of successful shots from the free throw line. Letter B, write a notation representing the whole problem. So the whole problem can be represented by a random variable x, which is binomially distributed with a mean of 20 and a probability of success which is equal to 0.85. Letter C, find the probability that a basketball player is successful with 1. All 20 throws. This problem could be represented by a notation probability where x equals 20. If we're working on paper 1 or even paper 2, we are required to show some solution. So it's going to be the combination 20-20, or 20 takes 20 times the probability of success times the probability of failure. So the probability of success is 0.85 raised to whatever is the value of x, and that is 20, and then 0.85, 0.15 raised to 0. So that's going to be n minus x equals 0, or 20 minus 20 is 0. So you can get your calculator. You can follow the same format. We get the combination, and then you raise 0.85 to 20, and then 0.15 to 0, which is simply 1. You will be getting 0.03876, or probably some more decimal numbers. Or you can simply go, since you're working on your using your calculator, or you're using your GDC, you can go to binomial PDF and then encode the data given. It will still give you the same result. Now we have to write our final answer in 3 significant digits. So we shall have this answer is approximately equal to 0.0388. Let's talk about C, number 2. Find the probability that the basketball player is successful with at least one throw. So when we say at least one, we can have more than one. So 1, 2, 3, 4, and the maximum is 20 because the ball is thrown only 20 times. So to write that as a notation, this is the same as probability of x is greater than or equal to 1. Then we get, this is actually equal to probability where x equals 1, plus probability where x equals 2, plus probability x equals 3, plus the probability where x equals 4, until probability where x equals 20. So you can do that one after another, and you can use this combination 21, 22, 20 and 3, 20 and 4 until 20 and 20, and then you just replace the probability of success and failure. You replace your exponents with the corresponding x and x value, and for the probability of failure, it's gonna be n minus x, or 20 minus whatever is the x value. So you do it that way. It's quite long. And the shortcut, of course, is using your GDC. You go to your menu bar, probability, distribution, and then you choose binomial CDF, because this is cumulative. So you enter your lower limit, which is 1, and the upper, of course, is 20. This is discrete value, so those 1 and 20 are given as your lower and upper limit. The alternative solution for this one would be, since the values of x range from 1 to 20, then it only excludes 0. So another way of solving this is 1 minus probability where x equals 0. Now, the best thing here is when you get your probability where x equals 0, you can write it, or you can store the value of your probability where x equals 0 as, let's say, a. So you assign a variable a for that. So the next step will just be 1 minus a, because you have already stored the value of p probability that x equals 0. Just the same, your answer shall be 1. For letter C, number 3, we find the probability that a basketball player is successful with at least 18 throws. When we say 18, at least 18, can we have 19? Definitely yes. So we can have 18, 19, and 20. So mathematically, this is the way we represent probability where x is greater than or equal to 18. And we solve this by getting the probability of each: probability where x equals 18, plus probability where x equals 19, plus probability where x equals 20. In all this, when you are using GDC, you use binomial PDF, where x equals 18. then when x equals 19, then when x equals 20, and then you get the sum of all these probabilities. Or by using the formula where we use combination times the probability of a success over how many of that success, and then probability of failure, which is the remaining part of the total number of items. And then you get all of this from 20, combination of 20 and 18, then 20 and 19, and then 20 and 20. By using your GTC, you can have probability of, or binomial probability CDF, where your lower limit is 18 and the upper limit is 20. The answer is 0.404896, and that approximates to 0.405, three significant digits. In part 4, we are asked to find the probability that a player is successful with at most 15 throws. So when we say at most 15, can we have 16? No, right? So we can have only 15 going to the left, 14, okay, 13, and so on. So it's actually the probability of getting an x equals 0 plus probability of x equals 1, and so on until probability where your x equals 15. Then you can use the combination 20, 0, 20 and 1, 20 and 2 until 20 and 15. And then you just follow the formula that is equal to the combination times the probability of success times the probability of failure. So our probability of success is 0.85. Our probability of failure is 0.15. You just change the exponent of each based on our formula. Or the easiest way, of course, is using your GTC. You go to binomial CDF because this is cumulative score. Your lower limit will be 0 and upper limit will be equal to 15. The answer is 0.170153, and then we round our final answer to three significant digits. That's approximately equal to 0.170. Next, we find the probability that a basketball player is successful with between 14 and 17 inclusive throws. So it means that we include 14 and 17. Mathematically, this means probability where probability of 14 less than equal to x less than equal to 17. We solve this by getting the probability where x equals 14 plus probability where x equals 15 plus probability where x equals 16 plus probability x equals 17. Or we use the formula. You can follow the formula for binomial distribution. So we use our graphic display calculator, TI Nspire CAS or NANCAS. And then our probability will be equal to 0.573169, and then we round it off to three significant digits. So finally, we have an answer which is 0.573. Finally, for this problem, we find the mean, the standard deviation, and the variance. Our formula for the mean is simply n times p. So that gives us 17. For the standard deviation, the formula is the square root of npq. So that gives us 1.59687. Rounding it off for estimating this to three significant digits gives us 0.160. And for the variance, we simply multiply NPQ, that gives us 2.55. Let me read the problem. A factory has two machines A and B. The number of breakdowns of each machine is independent from day to day. Let A be the number of breakdowns of machine A on any given day. The probability distribution for A can be modeled by the following table. First question, find K. To find K, you get the sum of all the probability equated to 1. So we have 0.55 plus zero point 0.3 plus zero point 0.1 plus K must be equal to 1. Therefore, our K is equal to 0.05. First problem for B. A day is chosen at random. Write the probability that machine A has no breakdown. Machine A has no breakdown. We just look at the table and find the probability where there is no breakdown. So the answer is 0.55. Second problem. 5 days are chosen at random. Find the probability that machine A has no breakdown on exactly 4 of these days. We already know that the problem is binomially distributed, having n as a number of cases equal to 5, and the probability of success here is 0.55. That is the probability of not having any breakdown. So we look for the probability where x equals 4. We follow the formula. So substituting the values for the formula, we have 5 choose 4 times 0.55 raised to 4 and 0.45 raised to 1. It gives us an answer which is 0.205889. And finally, we give our answer into 3 significant digits. We have 0.206. This is a combination of the previous problem. Let me read. Let B be the number of breakdowns of machine B on any given day. The probability of B occurring can be modeled by the following table. Question letter C. Find expected or expectation of B. So here we're going to use the formula summation of all n times P. So we have 0 times 0.7 plus 1 times 0.2 plus 2 times 0.08 plus 3 times 0.02. The answer is equal to 0.44. On Tuesday, the factory uses both machine A and machine B. The variables A and B are independent. This is the question. Find the probability that there are 2 breakdowns on Tuesday. If you're going to use both machine A and B on a particular day, which is Tuesday, let us try to find the possible combination where there will be only 2 breakdowns. So I highlight them here in blue. So it could be that A and A, B and B, or A and B. When we say A and A, that means there are 2 A's for that particular day and no B. Same with B and B. That means 2 machine B's or 2 machine from B's, and then there's nothing from A. And then for A and B, 1A and 1B. So let's try to find out the probability of having 2 machine A's and no B. So we look at the table. Here we have the table for A, which is in peach color. The probability of getting 2 A's is 0.1. And no B, we look at the blue table, it's 0.07. And then next is having 2 B's, so we look at the blue table. Probability of getting 2 B's for that particular day is 0.08. And no A is 0.55. Now, probability of getting 1A and 1B, 1A is 0.3, that is in the peach color table, and 1B is 0.2. You can find it in the blue table. So this means A and A or B and B or A and B. So that means we're going to add all the probabilities. So the sum or the total of all these probabilities is equal to 0.174. Now for question number 2 of part D, given that there are exactly 2 breakdowns on Tuesday, find the probability that both breakdowns are of machine A. So how do we write that as a notation? So take a look at the computation or solutions which are written in purple color. So we can write this as a probability that you have A equals 2 or two machines coming from A given that there are two breakdowns is equal to, so the intersection of the two is, or having two machines from A is, which is this has already been solved a while ago, 0.1 times 0.7. And the probability of having two breakdowns from this answer uh, will come from your answer in D part 1. So it's equal to 0.174. Now calculating, the answer is 0.402299, or this is approximately equal to 0.402.